We are on to part 2 of our video for this week. This is the rest of the logarithmic properties. The first property that we're going to talk about is if you have a log base a of x in an exponent. Notice the base is a on the log, and there's a base a in the base. Log's an exponent. Log base a ends up canceling, and you get x. Log base a of a to the x is also x. And it may be because you might remember that if you have log base a of a, that is 1. And if you have log base a of a to the x, the x goes to the front. Okay, same thing for base e. If you have e to the ln of x, it's because it is e to the log base e of x. That's why the answer is x, for the same reason we just discussed above. And if you have ln of e to the x, again, that answer is x also, for the same reason. They also have a change of base formula. If ever you need to change the base from log base a to a different base, you would use this formula. In this case, they're changing log base a of x to ln's. Notice you put ln of x on the top, and you put ln of a on the bottom. So I always think about it as the bigger number is over the smaller number. Remember, as I said, this formula could work even if you wanted to change to a different base. So if I had log base a of x, I could change it to log base b of x over log base b of a. I could even make it log base 10 of x over log base 10 of a. Let's use these properties to simplify these 3 examples. Here, we can take the 2 and we can move it back up as an exponent. I also know that square roots and squares cancel. And I know that ln of e is 1 because it's log base e of e. Second problem, I have ln of e to the 2 ln of x. Remember, this is log base e of e to the 2 ln of x. Log base e of e can cancel. And the 2 could go back up and make an exponent. The next one, this is the same thing as 3 squared. Log base 3 of x. You could multiply these 2 exponents together, so you have 2 log base 3 of x. Again, the 2 can go back as an exponent. And when you have a base 3 and you have a log base 3 as an exponent, those 2 things cancel. These 2 exponents, Here is an example from your textbook in which you need to use different properties of logs. If you have $1,000 invested in an account that earns 5.25% interest compounded annually, how long will it take the account to reach $2,500? Well, remember from the example we've seen previously, this means that the P in the problem is the $1,000. The R in the problem, we have to take 5.25% and make it into an appropriate decimal. So it's 0.0525. We're compounding annually, so that's good to know because that interest rate is being compounded annually. And we want to know how long it will take the account to reach $2,500. So the $2,500 is the final amount in the account. So we know that the formula we are using is A equals P times 1 plus R to the T. We know that the interest rate is 0.0525. We know that A is 2,500, P is 1,000, and we can add 1.0525. And then the dilemma that you face is, how do you solve for T? So many professors talk about it as you're trying to get T as an exponent out of the exponent position. So whenever you have a variable in an exponent, you can get it out of the exponent by taking a logarithm on both sides of the equals. Now you can use any logarithm that you want. I am using, oh, before I do that, because right now that 1,000's in the way. That's not good. Let's fix that first. Let's get rid of the 1,000 because we're trying to isolate T and it's right now in an exponent. So let's divide by the 1,000. That's much better. You get 25 over 10. 25 over 10 is then reduced to 5/2. And now I'm going to take a logarithm on both sides of the equals. What that does is now we can use that exponent rule that says that T can go to the front of the logarithm. And I can divide both sides by ln of 1.0525, and that will isolate the T. Now you just pick up your handy dandy calculator, you throw ln of 2.5 divided by ln of 1.0525 into your calculator, and you get T is approximately equal to 17.9 years. So because we want the end of the year mark, we will say that this happens in 18 years. This section in your book also talks about inverse trig functions. So in this case, you need to keep in mind that an inverse trig function is, it undoes basically the regular trig functions. And as we discussed, inverse functions, the domain becomes the range and the range becomes the domain, and vice versa. So for example, y equals sine x. It looks like this first one right here. In order to find an inverse of y equals sine x, remember it has to be 1 to 1. So that means that we need to cut off the sine x so that we don't have it not being 1 to 1. Remember that it typically would continue and it would look like this, but now look, now it's not 1 to 1, right? So that's a problem. So we're going to limit the domain as I did here. The domain's going from negative pi over 2 to pi over 2. And the range then would go from negative 1 to 1. Now we would be okay to do sine inverse of x because we have limited that domain. And now the function's 1 to 1. They also call sine inverse of x arc sine x. So if you see y equals arc sine x, you know it is the same thing. So the key to these problems is remembering that we have to cut off the domain in order to be able to get an inverse function. Cosine is typically cut off between 0 and pi, and the range again goes from -1 to 1. That is so we can then do cosine inverse. Tangent goes from -pi/2 to pi/2. Range goes from -infinity to infinity. Again, we're cutting off the domain so that we can then have a one-to-one function, and we can talk about tangent inverse. Less commonly used, cotangent, secant, cosecant, but the information's here in case you need it. These are what the inverse trig functions look like. Notice that the domain and the range from the original trig functions have swapped places. So originally, the domain and the range of sine, the domain was from -pi/2 to pi/2, and the range went from -1 to 1. You notice that the domain and the range in an inverse trig function flip places. This is what arc sine looks like. This is what arc cosine looks like. Again, domain and range flip places. So you need to remember that your domain and your range are limited. Okay? So let's look at the examples. I've got an arc sine example and an arc cosine example because these are the ones that usually you might see. Sometimes you see arc tangent, but it's very rare that a problem will have arc cosecant or arc secant. So here we're going to focus on the arc sine and the arc cosine. So first of all, remember that everything has switched positions. So originally we would have y equals sine of some x. Well, when we take the inverse, we would have x equals sine of y. And then we take the inverse sine on both sides to get it by itself. And that's where the sine inverse comes from. So when they ask you about sine inverse, they are asking you actually about what is the ratio. Or they're actually asking you when you have the ratio here, so the answer of the trig function, they're asking you what's the angle. So you're going backwards. You're trying to find the angle instead of the ratio. Let me make that more specific. Let's look at the first example. So arc sine, this is the ratio of the sides of the triangle that we're talking about. So our answer will end up to be some angle measurement. Okay? So a lot of the times you can actually do this in your head. And you have to think, well, what angle measurement would I be dealing with if my answer was square root of 3/2? And so automatically I remember that this must be a 30, 60, 90 triangle, because in a 30, 60, 90 triangle, your ratio would be 1 square root of 3, 2. That's the ratio of sides. And so we know that sine is square root of 3/2 when we're talking about the 60-degree angle. 60-degree angle, by the way, is the same thing as pi/3 in radians. Now, we've got an answer of what theta might be, but remember that there are possibly other places where your ratio of sides is positive. And for sine, the ratio of sides is positive in quadrant 1. It's also positive in quadrant 2. So let's see if we can use both those quadrants or not. So you would go back up here, and you notice that the range, the angle measurements of arc sine have to go between negative pi over 2 and pi over 2. Negative pi over 2 is down here, and pi over 2 is up here. So I would need to stay on this side of things in order to be able to get the answer. So that means we must be in quadrant 1, because in quadrant 4, sine is negative down here. So the only answer I can get is pi over 3. Let's look at arc cosine. So first of all, I have to think about what kind of triangle would make cosine ratio come out to be a half. That happens, and again, in a 30, 60, 90 triangle. Because again, the ratio is 1 square root of 3, 2. And out of this situation, I would come up with a half if I was talking about the 30-degree angle. So my theta must have something to do with a 30-degree angle. Now, notice the ratio of sides here is negative. Ordinarily, cosine is negative in quadrants 2 and 3. Cosine is positive in quadrants 1 and 4. So I must be talking about either quadrant 2 or quadrant 3. So let's look back up at our little thing up here, and I'm looking at the arc cosine. And I need to look at the range, because that's talking about my angle measurements. And this is saying that the range needs to be from 0 to pi. 0 to pi. 0 to pi is here. So we know we cannot be here. This would be a no, because cosine's not negative there. So it must be that we have a 30-degree reference angle over here. Since 30 degrees is pi over 6, I know that I'm talking about theta, or x, whatever you want to call it, being 5 pi over 6, because that is between 0 and pi.